So, good morning, everyone, and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Pedro Reis from Ecole Polytechnique Fédérale de Lausanne in Switzerland, and two of his colleagues as well, Paul Johanns and Paul Grandgeorge. Pedro did his PhD at the University of Manchester. Before this was after an undergraduate degree also at the University of Manchester and a postgraduate degree at the University of Cambridge. He then followed on with postdocs at City College of New York and ESPCI in Paris, after which he joined MIT in the US, first as an instructor and then as a faculty member. And more recently, he's moved to Switzerland, to Lausanne, where he is now based. And today he's very kindly agreed to take us on a virtual tour of his lab at EPFL. So before I hand over to Pedro and his colleagues for the truly interesting stuff, just a couple of announcements from me. First, this seminar is being recorded, so by staying on, you're giving consent to your voice and image being recorded and stored. Second announcement is, in the interests of internet stability, can I ask everybody, except the speakers, of course, to mute their microphones and switch off their cameras during the seminar. If you wish to ask a question, which you can do, indeed you're welcome to do at any point during the seminar, you are of course free to unmute yourself and switch on your camera. So without further ado, it's over to Pedro and his colleagues for the seminar.
Muito obrigado, Paulo. Obrigado a todos. So as I was telling Paulo earlier, it feels a bit strange to be speaking in English to the compatriots, but since my two team members only know a little epsilon of Portuguese, I think will be easier for everyone. Actually, that's an excuse because I left Portugal more than 25 years ago, and so giving a technical talk in Portuguese would actually be quite challenging since I did all my studies abroad. Anyway, excuses aside, and so yeah, we try to do something a little bit different. I'm sure you're all tired of listening to 15-minute long Zoom talks, Zoom monologues, and so we try. The goal here is to frame it as if you had come to visit us in Lausanne, and if we were able to show you the labs, and of course we also want to talk some science. And along the way, if you had been visiting, or of course you'd be interacting with some members from my group, but so that it doesn't come across as a random collection of topics, we've decided to really frame the talk, the visit around the topic of elastic rods and knots. So I have a background in physics and then transition into the world of engineering and engineering mechanics, but always with the perspective of curiosity-driven research. And so I tend to use the slogan of science-enabled engineering and engineering-motivated science, and so that's what we will try to convey today. So a mix of topics that are relevant for applications and also things that we just do because we can, and that we don't, of topics we don't understand. So we go on to the next slide. So maybe to highlight this virtual lab tour aspect. So I'm going to teleport you from your campus. Well, probably some of you are sitting at home, but probably not so far from Cidade Universitaria. And we're going to go across Spain, through France. We won't talk about football today. And welcome you to Lausanne. And so just a little parenthesis, Lausanne has an enormous Portuguese community here. And so actually moving from Boston to Lausanne felt to some extent like coming home, just because there's so many Portuguese here in Switzerland. Okay, so this is our campus. It's a modern university. The current format of the university as a federal institute is quite recent, is less than 50 years old, and so the buildings go along with it. And so if you go on to the next slide, maybe let's just give you a little idea of the surroundings, which are spectacular. So we're right next to the big mountains, to the Alps. Well, when people visit and they see the mountains in front of us, they say, "Oh, Switzerland is beautiful." Actually, the mountains you see in front are all the French Alps. So you have to look to the left to see the Swiss Alps, but that's a little detail. So Switzerland is at the end of the lake towards east. And then towards to west and towards east. At the end of the lake, you have Montreux. Maybe if you like jazz, you've heard about the Montreux Jazz Festival. And then, so what you're looking now at the Swiss Alps with Lausanne, the city in the background. So it's a small city, 120,000 people. So it's a small little place, and we're about 5 kilometers away from Lausanne. Okay, what you saw actually just the building with holes, that's the iconic building in our university, is the library. And the building you're seeing right in front is our building for the School of Engineering, with a primary focus on mechanical engineering. We call it the MED building, and we're right on the ground floor. And so what I encourage us to do now is to go on a little tour of the labs. And so we of course, this is not live. We took these videos beforehand. So let's go for a walk. So if this works, we're now stepping down from the auditorium, which is a nice place to have lunch, and we'll enter our lab spaces. So our lab is primarily experimental. We really have as a starting point experiments, which then of course we complement with a fair amount of theory and computation. And our lab is divided into 4 spaces. This is what we call the big lab, well, because it's big, but also because this is the versatile space that we use to build our own experiments. The other lab spaces are a bit more dedicated. We have a fair amount of mechanical testing, and the experiments you'll quickly see that they're mostly custom made. And so not quite standard equipment that we have to build and fabricate. And so we have a fab lab where we do a lot of these constructions, so a mix of digital machining equipment like laser cutters and water jets and whatnot. And then actually I won't have much time to talk about magneto-elastic structures, which we magnetize using these this system that you're seeing on the left, a bunch of 3D printers. And so basically to have the versatility and the ability to build our own things without having to rely too much on professional workshops. So we're very hands-on. And then we have a chemistry lab where we do a lot of the polymer synthesis. And then behind the chemistry lab, we have what we call the imaging lab for characterization of geometry, since we focus so much on reconfiguration of structures. What you saw just there is an X-ray micro computer tomograph, so a micro CT, of which we'll be showing some results. And then we have a bunch of profilometers. And so imaging and characterization of the nonlinear geometry of these systems is central to our data acquisition. And having a micro CT that we can use 24/7 is something quite unique, and we're making extensive usage of that. And the building is spectacular. It was built just a few years ago, same architect as the Bibliothèque de France in Paris, and with these interconnected staircases and bridges, actually enhances interaction within the building and the various groups. So maybe let's actually tell you a little bit more in detail of what is the research approach and the topics that we focus on in our group, the Flexible Structures Laboratory. So as I said, I do have a background in physics and statistical mechanics. And halfway through my postdoc experience, I became acquainted with structures and especially structures that can undergo large reconfigurations as a result of buckling. And that has been my central topic of research ever since. So of course, we're really at the interface of mechanics, physics, and engineering. In engineering, the typical perspective is to design structural systems that are as lightweight, or one of the approaches that are as lightweight, as strong as possible. And what we always try to avoid are critical loading conditions. Of course, there's many different ways in which structures can fail, fracture, plasticity, or elastic buckling, right? So, and we'll be focusing a lot on buckling later on. And of course, predicting critical buckling conditions is challenging, and that underlies a lot of the components in design codes for mechanical systems or for civil engineering systems. And what we try to do is to take a bit of an alternative point of departure of saying, okay, yes, you have the critical buckling conditions, but let's go beyond buckling and make use of the reconfigurations that can ensue as a result of buckling for new stuff, for perhaps new functional modes of deformation, or perhaps even just for curiosity-driven research that might be inspired by biological systems. And there's a lot of biological systems that can work in the post-buckling regime. And so it's this yin-yang between fundamental questions, I mean, fundamental inverted commas, we're not talking about particle physics or black holes here, but yeah, so curiosity-driven questions and engineering applications. At the end of the day, we are an engineering lab, and we have a wonderful team with a mix of postdocs and PhD students. Okay, so next, in terms of systems, when we talk about slender structures, which is really the primary class of systems that we look at, we can classify them and divide them into three big buckets, just according to geometry and aspect ratio of the various geometric dimensions. And so these buckets are rods, plates, and shells. So rods being systems that have a dimension that is the length much larger than the other dimensions in the system associated with the cross section, like hair or flagella of bacteria. And the other class of systems is plates. So systems that have a length scale, the thickness much smaller than the NL length scale in the problem. And then shells are similar to plates, but they have finite curvature at rest. Okay. And so what's wonderful about these systems is that there's a prevalence of universality in terms of scales. And so the mechanisms and the processes and the questions that you ask at one scale, perhaps at a kilometer, like some examples we've worked on coil tubing operations in horizontal well bores or deployment of cables in the ocean, the kind of tools that we develop and the equations that we have to solve are essentially the same to the underlying equations of a carbon nanotube or a flagella in a bacteria, right? And so this ability, and for example, for plates, actually showing you another example. So we've quite some time ago, we've worked on the tearing of graphene sheets, which follow a mechanism that is nearly identical to what happens when you tear Scotch tape from a roll of Scotch. So here, many different orders of magnitude above that of graphene, and the same plate equations are what is used to describe the draping of a curtain, right? So really jumping and walking across length scales being central to our research. And so as a result of this importance of geometry, what I would say is the secret sauce in our lab has been to devise an experimental methodology to scale down, if we're talking about kilometric relevant problems, into the centimeter scale, the finger scale, as I usually talk about, or upwards, if we're coming from graphene and carbon nanotubes, also again to the centimeter scale. And then we perform these precision, so we jokingly call them PDEs, not PDEs in the mathematical sense, but PDEs for precision desktop experiments, which sometimes we even refer to them as experimental theories, right? We really try to nail the mechanism by getting rid of all spurious ingredients that are irrelevant, which is what you'd be doing if you're trying to come up with a theoretical description of these kind of problems, right? And so, yeah, these experiments are central to our study, but to our studies. But of course, then theory and computation is also a very important part of our ingredients. Okay, so next, yeah, realize running a bit out of time. So just let me give you 3 very quick pointers of other problems that we won't talk about today. And so over the past few years, we've gotten very interested on magnetoelastic structures, so structures that make use of the coupling between elasticity and magnetism. Many different kind of problems that we've been looking in this respect. So here I'm just showing you an example of an actuated helical structure by the application of a constant gradient field that induces internal forces into this rod. And another example, perhaps closer to applications, a recent paper we had out on programmable metamaterials with stable memory, where we make use of bistability of shells and magnetic actuation to arrive to those systems. So closer to engineering, we're very interested on how shells buckle. So if you have a thin shell like a fuel tank or a radome, and you ask, okay, given a certain load, when do they buckle? Well, that's actually a very difficult question to predict because these systems are strongly sensitive to imperfections. So we've been focusing extensively on the role of imperfections in these systems. And I also like fluid mechanics very much, even though our emphasis is mostly on solids and structures, but we do a fair amount of work on fluid structure interaction, especially in the context of flight and considering the structural aspects of flexible foils and wings in the aerodynamic performance. Okay, so but today, what I really want us to focus on is on a set of problems, or a subset of problems that we have looking at on the mechanics of rods and knots, where friction and contact are two important ingredients that cannot be neglected. And a lot of the work we'll be presenting has been spearheaded by Paul Grandgeorge and Paul Johanns, who will be sharing some of their results in a second. Okay, so maybe last slide of context. Why do we care about knots? Well, first of all, because it's a very challenging problem, and so the interest, and I do have a comment on what are the fundamental challenges in this class of systems, but they really matter, and they matter. But you might ask, well, but we use them. Who cares? Well, a lot of the knowledge that we have developed for these systems is primarily empirical. People have been using knots and ropes for millennia. And so we just know kind of do's and don'ts for these kinds of systems. But to come up with predictive models of the kind of work that you all do, that is a fair amount more challenging. Why do we care? Well, they are very important for sailing, for climbing, for textiles, for belt-driven machines. And a primary drive that we also actively working on by interacting with surgeons is also the mechanics of sutures and surgical knots, and being able to come up with predictive models, for example, to inform assisted robots in semi-autonomous procedures. So this is actually central to the PhD thesis of Paul Johanns. And next, Paul. Okay, so maybe last slide before there's one on fundamental challenges. Okay, so there's really three primary ingredients that make these problems very challenging. The first is buckling. So buckling is an instability that happens when a thin structure is loaded by a compressive load. And as I was saying earlier, predicting the critical buckling conditions goes back to the days of Euler in 1744 with his famous paper on elastica. And the problem that happens past these critical buckling conditions are reconfigurations that are strongly geometrically nonlinear. So let me illustrate what I mean by geometrical nonlinearities. You grab an elastic rod and you apply it under tension. And yeah, stress strain curve for these elastomeric materials is linear up to 10%. And so this is first year physics, maybe even high school physics, fairly simple. Well, if you start thinking about finite strains, then the theories become a little bit more sophisticated, but all very standard. Now, if you plate this rod under compression, and perhaps here I'm adding a little bit of twist, then you have buckling, but not only you have buckling, you can have multi-stability coexistence of solutions with subcritical bifurcations. And this is really caused by the underlying nonlinear geometry. Okay, so these are the kind of things that really call for the full toolbox of nonlinear dynamics and nonlinear physics to describe these systems. In addition to these geometrical nonlinearities, in many systems that involve rods, we have to deal with contact. Even without friction, that's already a strong hard nonlinearity. Maybe let me just, so here I say that it's important to consider contact and friction. And even taking simple Coulomb-Hamilton, when you couple it with contact and you couple it with geometrical nonlinearities, it becomes a full kitchen sink of nonlinearities that we have to deal with. And when we have nonlinearities, as you know, in this class of systems, unexpected things happen. And that's why experiments for us are very important, because they allow us to jump into that jungle of unknown nonlinearities and uncover mechanisms that then we try to rationalize. So again, with experiments taking a primary role in setting the line of research. Okay, so blah 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 out of the way. Let's get to the bulk of what we want to tell you about today. So if you move on to the next slide, and so specifically on these rod-like systems, if we have a knot, maybe go back to the previous slide, Paul. If you have a knot that you tie and it holds because of friction, In these systems, I want to highlight with this video that Paul Grandgeorge produced that friction is crucial. So here, of course, the rod would like to be straight because that would minimize bending and gravitational energy. And friction induces resistive forces that, of course, prevent that. Now, if you lubricate this very same rod with the very same figure of 8 knot, again, here, friction does not do the job that it needs to do. And essentially, the knot becomes undone because, again, that's the minimum energy state. These are the kind of ingredients that we'll have to be dealing for the rest of this talk. So friction is key. Okay, so very quickly, we want to highlight 3 specific projects today. First, the classic elastic capstan that Grandgeorge will modify in a way that in ways that were not really understood previously in the literature. And if you're not familiar with the capstan problem, Paul will give a brief introduction. Then we'll ask, well, instead of having a rod wrapped around the rigid cylinder, what if the other element on which it's wrapped around is also flexible with tight curvatures? A very exciting study that we completed recently. We'll find that geometry is central to that problem. And then we'll actually go back to the applied math and knots community and ask how robust are some of these geometric arguments in real physical systems. And so Johanns will be covering some of that towards the end of the talk. So Grandgeorge, all yours now.
Cool, thanks. Okay, so I will tell you a bit about this capstan problem that Pedro introduced in the elastic case. So maybe some of you, as a sailing country, as Portugal, you know a bit of the capstan problem because it's related to ropes and sailing in general. So typically, the capstan problem is if you have a rope that is tied around a cylinder like this, the question is, what is the tension that you can apply at this end as a function of some lower tension that you're actually applying to the other end? And maybe a good representation of this is here. This is actually a capstan that allows you to wind the rope around the rigid cylinder. And again, the question is, well, what is the higher force as a function of the lower force that you're applying to the rope? And this is not only applicable to sailing, it's also for, well, driving mechanisms where you have a driving pulley that is through a belt generating motion to a driven pulley. And here again, you have a low force here and a high force here. And well, the big question is from a theory point of view in this kind of system, what is the ratio between these two forces? And actually, if you take the limit of a perfectly flexible belt with no thickness, you find a straightforward relation between the ratio. So for the ratio of two forces, which is given by this exponential here of the friction coefficient times the wrapping angle around the cylinder here. So here again, you have to take into account that there is sliding and you're asking what is the ratio of the forces. So we might think, well, this problem seems pretty well put and already solved from a theory point of view. But of course, there are assumptions to this that are, well, perfect flexibility and no cross-sectional thickness. So we thought, okay, but in real systems, well, the ropes, they might have some rigidity to bending. They might have some thickness compared to the cylinder of the radius. So the theory might not hold entirely. So we thought, okay, let's design a system where we can actually measure the ratio of the force. We have a rod here that's made out of a very elastic polymer and is wrapped around a rigid cylinder. We hang a mass here that will be this dead load, so the small force. And then as we pull the cylinder up, as you'll see in a minute, we will measure the force that is being applied at the other end. So really, we're probing what is the load transmission along a rod when it's sliding in frictional contact with this rigid cylinder. So you saw the video, and this is the type of force curve that we obtain, so force versus displacement. And you see here, well, this is actually the low force that I'm applying, and this plateau force here, as soon as sliding is happening, well, this is the higher force. And you see, well, they're not equal because friction is generating tension increase. And actually, we can represent this ratio here that I'm interested in, the higher force divided by the lower force, as a function of the loading on the system. So let's say the lower force that is here normalized by the typical axial stiffness of the rod. And we can do this for several dead loads, and we obtain actually a complete curve that tells us how the system transmits the load as a function of how much it is loaded by this dead load, F0. Okay, And so, of course, we directly want to compare this with what finite element method would tell us. So here, I'm just going to show you a quick video of how we can do this with finite element. So this is actually, the computations have already been performed, and you see here there is a cylinder and a rod wrapped around it. And actually what I'm doing now is I'm rotating this cylinder in this direction. And so you see that there is some frictional, you don't see it, but there is some frictional interaction here. And there again, the question is, how does the force transmit through the rod? And of course, everything is dictated by the contact region. And what we're surprised to see is that if you look at the contact pressure between the rod and the cylinder, well, what you see is that it is strongly inhomogeneous. And there are some regions of higher pressure that you see here. So this is actually the entrance of contact. There's really much more pressure at this location than somewhere else. So already we see that even though the system looks rather simple, it shows some non-trivial behavior locally. So we'll try to go a little deeper into this. Okay, so we did some experiments, we did some numerical FEM, we can compare them. So experiments are the data points, and the FEM is this line here with the shaded region for uncertainty. And we could do this for different diameters of the rigid cylinder. So this small d here is actually the ratio of the cylinder diameter divided by the thickness of the rod. So we normalize the system. Okay, we can do this for d equal 10. So for a smaller cylinder, d equal 5. And we can go even smaller down to say that the thickness of the rod is equal to the diameter of the rigid cylinder. Okay, and well, as I said, there is a theory existing for this that I told you about earlier, the classical Capstone analysis, the classic Capstone equation, which has some assumptions underlying it. And what we see is that, well, this theory, it predicts that the force ratio should be on this dashed line here. And obviously, we see that experimentally, this is not what we observe at all. And also that this theoretical prediction, it tells us that the ratio should not depend on the diameter, whereas we see very clearly that actually it does experimentally. So, of course, the reason behind this is that, well, this theory here has assumptions that are not true in reality. So flexible stiffness, but also a thickness of the cylinder of the rod. Sorry. So some assumptions are broken. And actually in literature, it has been, this problem has been studied with some assumptions that were taken into account, but never in a complete set that we could actually compare directly with the experiments that we are doing at the lab. So we needed to come up with an augmented model based on the Kirchhoff rod model. So basically a one-dimensional or reduction down to one dimension of elasticity. And here you see the schematic representation of the system. And well, we wrote the equations related to kinematics. We apply a force and moment balance locally at each location of the rod. And then we use a constitutive bending law that relates the moment inside the rod as a function of its local curvature, theta prime here. And actually, if we do this, we end up with a big system of ordinary differential equations that we can solve using the MATLAB function that's actually very robust, this BVP5C. And well, typically we get this type of curves along the arc length of the rod. We're quantifying the local tension in the rod, so really the tension that the rod is feeling. And if I travel along the rod, so from S equals 0 to S equal L, you see that I start at the given tension. And then as I enter the contact region, this tension starts increasing due to the buildup, due to friction, right? Up until a point where then it reaches the other end of contact, and there it reaches, in this region here, the tension is constant because the filament is straight. And so we get this purely theoretical curve, right, with no adjustable parameters, and we can compare this with the FEM results that I showed you earlier, where we also quantify tension along the rod. And you see, well, that theory does a fairly good job at predicting what FEM actually tells us is happening exactly. Okay, so right, if we go back to this pressures curve that I was referring to, the force ratio as a function of the loading on the system F0, we can compare experiments in FEM with this theory that I just told you about. And you see that it's almost exactly the same for large enough diameters of the cylinder, for d equal 10, for example. And if we go to smaller diameters, d equal 5, well, we see that this agreement is still pretty good. So theory, dashed line, FEM, solid line, still fairly good. But if we go to smaller diameters, so if we go, for example, to d equal 2, so, or even d equal 1, well, then we see that theory starts failing drastically, and we're not able to represent the mechanics anymore that well. So quick summary, theory is satisfactory for large enough cylinder diameters, because this is where curvatures are not that extreme, but then theory is limited for smaller cylinders. As the curvature that is induced, well, it induces finite strains that are no longer within the elasticity theory of the Kirchhoff rod theory. Okay, so good, not so good. And actually in this region here, where the thickness of the rod is of the same order as the thickness of the cylinder, well, this is actually very relevant to knots, right? Because knots are nothing but, say, an entanglement of rods that are in contact with one another. So curvatures are pretty extreme. And this is actually what we'll move on to next. How can we describe the mechanics of knots when curvatures are that extreme? And for this, I will let Paul Johanns tell us about his beautiful shoe here. And actually, there's a lot of interesting things to say here.
Right, thank you so much. So yeah, indeed, this is the classic square knot, the classic knot you would do in your shoelaces. And what you can actually see is that, well, this is a very tight knot. And what does a tight knot actually mean? Well, the diameter of the filament and the characteristic radius of curvature, they are of the same order of magnitude. And so the existing theoretical models would actually not work anymore for this, these tight configurations. And so we want to get some understanding about these contact regions. And for that, we are going to break it down in the next slide, where we take probably the most simplest knot, an overhand knot, an open trefoil knot, and look at it a bit closer. So you can see on the left two highlighted regions. Maybe you can go a bit back, Grandgeorge. Two highlighted regions where we have like an interaction of two strands of the filament, and that are actually just in contact. And this we can also observe in simulations. So this is a simulation that was done by Chang-Yap Baek very recently, who was a former graduate student in our lab and who is now a postdoc at Harvard University. And he came up with a numerical framework to well, in finite element method in Abacus to model these kind of knots. And so during this tightening process, we can actually see that this entanglement of the filaments is still there, and the contact becomes tighter and tighter. And so this is actually something where we can break the knots down and make the problem hopefully a bit easier. And this leads us then to, well, the next main chapter, where we will talk about the clasp of elastic rods. So we call this a clasp when we have two elastic rods that are in tight orthogonal contact. And the system is actually quite easy, or looks very easy. So you have two rods, two ropes, two filaments in tight contact with a certain opening angle. And but now we will look a bit closer, and we will see some very surprising facts about this. And so what is a clasp? Well, you have it here on the left-hand side. It's a model system of two rods that are crossed orthogonally, and we use hyperelastic material, these elastomeric silicon polymers. And what we impose is a rod length, diameter, boundary conditions, and we'll also make it slide and measure the friction. And this was detailed very recently in the paper by Grandgeorge and Baek et al. And we'll go now through the main points of this. So the main goal is to characterize, or to get some understanding about the contact mechanics and the load transmission for these orthogonal clasp with friction that is involved. Okay. So here again, the model system, you can see various parameters that we could change. And what we are most interested in is the contact region, so where the two rods are touching, but obviously we do not have access, we don't have a sight on it. So we would need like a non-destructive volumetric imaging to get access to it, and we actually do that with our micro-CT, which stands for microcomputed X-ray tomography. You can see here a volumetric image of this Clasp configuration. It's still just seen from the outside, and in a moment we'll go see what the contact region looks like. But before that, let's go to the imaging lab, and I will show you again our micro-CT, where we would put, for example, a knot on elastomeric structure inside. And I guess you're all familiar with the principle of a micro-CT, but I will detail it just again. We take this knot down to a rotation stage, and it is now being irradiated by X-rays coming from the X-ray tube. And in the end, we would end up with a whole stack of 2D images that are based on density differences. Okay, so let's do that for this figure of 8 knot. This is an optical image. Put it inside, we scan it, we do a 3D reconstruction, and we would get, well, what we see here rotating. And so this consists actually of a stack of 2D images that you can see on the right-hand side. You can see some contrast between the surrounding air and the knot, because the method is based on density differences. However, we are not able to tell the two touching rods apart, or we can't see any contact in this. So we have to come up with some technique in our fabrication of the rod, which is a coating, and will also include some insets. We're using another material, another elastomeric material that has a different density. On the left-hand side, you can see what we do, this dip coating, where we would pull our elastomeric rods through a polymeric bath with a constant velocity and up with a uniform coating thickness. And this material should have similar elastic properties, not to alter the overall mechanics. And yeah. Right, so here we have our cross-section image now, where we now can actually tell the touching rods apart thanks to the coating. And we also incorporate a physical centerline fiber to track the material centerline, and also a physical eccentric inset that I will show you in a bit what we are using it from. Right, so here we do some image processing of these CT data. This is the overhand knot, where we would go through with a triad of having a tangent vector and two director vectors. So one of these, or these director vectors, are actually used to track the twist. On the bottom left, you can see the material frame. So that's what we see on that plane that is iterating through the knot. And I would like to emphasize that this is actually experimental data that we can now use to describe also the clasp. And so I would give it back to Grandgeorge to use these tools on the Clasp configuration.
Great, thanks. So I'll tell you a bit more about this Clasp, which is a more evolved system close to the Capstone. So how will we study it? We will use the experimental analysis that Johanns just told us about. We'll also do some FEM on this. And finally, I will tell you a bit about a mathematical, purely geometric system that allows us to study this more as a conceptual idea and really understand it more fundamentally. Okay, so let me start with what actually Johanns just told us about. I have this clasp here, this clasp of two elastic rods, and I'm going through it thanks to this image processing. And this allows me to obtain the contact region between the two rods that I can then represent in this 2D map of each contact point is associated to the two rods at a given location along the rod arc length S1 and S2. Okay, so now I'm just defining the tools. You see we can have a contact map in 2D. Okay, now how does this contact map look like when we use FEM? Well, actually, if we do FEM on this, so we use a neo-Hookean solid to represent the VPS. Well, this is what we would obtain as we pull the two rods apart and we increase the contact region between the two rods. So you see here, I'm actually pulling here, and you see the contact region. We don't only have access to the contact shape, but we also have access to the contact pressure between the two rods. And this is actually, this contact pressure will actually be what I'll be telling you a bit more about. And finally, the ideal geometric clasp. So it considers two perfectly flexible tubes. So tubes as in they're just ropes that can perfectly bend. They're inextensible, they have no cross-section deformation, and they're called geometric because they have the geometric constraint of non-penetration. And this was a collaboration that we had here with the LCVMM group, so a math group at EPFL, that's led by Professor John Maddox, who we had a really nice collaboration with. And so what they do there is they have two tubes that are in contact, and they compute the contact shape between the two tubes. And surprisingly, this contact shape in this purely geometric setting, it is not a contact area, but it is a contact line that has this diamond shape that you see. So there is an air gap between the two cylinders as we tighten it. This might be surprising, but if you were to do it with your hands, you see if you tighten your hands like this, you get an air gap between your two hands. So if it works with your hands, it might work with cylinders. And this is actually the case. Okay, so at each location along one arc length, the other rod is in contact with 2 points. Okay, I'll try to hurry up a little bit and tell you about the results. So here is the experimental boundary of the contact surface that you see here in this SA-SB, so 2 arc lengths. And if we compare exactly the same configuration with what we found in FEM, well, we see that first, the boundary is very well respected, but also here we see already that we can quantify the pressure of between the two rods thanks to FEM. And we see something surprising is that it looks like there is some sort of ridge that connects the 4 peaks here. And this ridge, we can actually quantify it based on, if we look here on the 3D view of the pressure map, we see that there is a ridge that we can quantify very clearly, and it's represented here as a blue line. And finally, well, we want to compare this with the mathematical geometric system. And if we were to take the same opening angle between the two rods, this here would be the diamond-shaped contact line that mathematics or geometry predicts. So it's actually surprising to see that, it's a good surprise to see that the pressure seems to be dictated by some geometrical arguments, so purely geometric. So geometry acts as a backbone for the contact pressure. Okay, right, and so then we decided to also have more insight into the frictional properties of this clasp. So we have here a sliding rod that is in contact with a static rod attached to the wall. And this is of course the clasp. And there again, thanks to frictionless pulleys, we're going to apply a tension at one end whilst pulling at the other end and quantifying the force at the other end. So this is what the experiment would look like. You can feel or sense that the tension in this strand is higher than this one. And well, how the force gets transmitted is very important for the applications that we talked about, and typically knots that are nothing but, yeah, exactly, a series of entanglements like this. Okay, I'll try to go quick on this, but we get the typical force displacement curves as well. Then we can do this for several configurations of the static rod and the sliding rod. And finally, we get that the force ratio that I told you about earlier as a function of the lower force, well, it depends non-trivially on how you load the system. And interestingly, the more you apply a dead load, so the more the system is loaded, the more the higher the force ratio will actually be. So you transmit force a lot more when the system is under tension. And this is exactly because the two rods get more and more in contact through this intertwining. Okay, and we compare this, the obtained pressure maps based on FEM. We compare them to the mathematical model that John Maddox and his team developed, and we see a striking resemblance between the pressure maps observed numerically on physical system compared to the ideal shape of the linear pressure of this contact line between the two rods. So this is yeah, just the beginning of more understanding of how pressure gets developed in these systems. Okay, and finally, maybe Pedro, can you tell us what we'll talk about next?
So maybe making a link between what Grandgeorge was telling us just now about adapting the capstone problems for situations with tight curvatures when the substrate around which the rope is wrapped is also flexible with friction and contact. And we saw that geometry was really the backbone of these problems. And of course, the question is it just a fluke, or is geometry that robust? And hence the latter. Johanns will now give you very brief notes on the very similar findings observed for the case of ideal knots. So we went to the ideal knot math community and tried to do some precision experiments to again check how much is geometry really ruling the whole game. So Johanns, very briefly, we're running out of time, so we have like a couple of minutes and then we should really take some questions.
Yes, right. So there are actually very few studies on ideal knot configurations, and mostly in the math community. So again, we have this ideal rope model, and we would basically use these and compare or do physical realizations on our elastic rods and do a compare and contrast study to see how well they perform. So we have actually the full 3D elasticity. Maybe you can go a bit further, George. The full 3D elasticity, and let's directly jump to the open knot configuration, as it's a bit more functional, just for the sake of time. So we can do this in simulations. Okay, just go ahead. All right, so we have here this open knot configuration. This is the tightest configuration for the ideal one, and we would they actually, Pieransky and collaborators, observed a curvature peak right at the entrance and at the exit of this knot, as you can also see on the left hand side in the curvature profile against the arc length of the rod. And now we do our physical realizations of very tight elastomeric configurations, and on the right hand side you can already see that we actually observe in these outer segments, these shoulders of this open trefoil knot, the highest curvature, which is also represented by the number 3 on the left-hand side in the curvature profile. And well, we have a small curvature, like a local maximum, but it's clearly not the global maximum. So we can actually see that the ideal model is not including all the ingredients that are at play for elastomeric rod. Okay. So let's do some FEM simulations where we can get access to the contact pressure mapped here in this pressure map that you already saw for the Clasp configuration. And what you can take from this is that the contact pressure is very high all along the rod. However, in the next slide, we can see that there are regions where we have localized contact. So we define a circumferential contact length at each section of each material frame of the rod, and we can see that it's maximized right at the entrance and at the exit of this knot. And going further and analyzing the cross-sectional area at each cross-section, we can see that we have very pronounced constrictions right at the entrance and at the exit. And probably these elastic constrictions might be a precursor for structural weakening that are not captured by the ideal rope model. So we should be careful relying fully on the ideal rope models when dealing with purely elastic rods. Okay, and maybe the next slide, we have a little extra bonus where we would show you a topological observation. So this is the closed trefoil knot, so it's nothing else than taking the open configuration and closing it. So we do the CT scan, this is experimental data, get access to the material center line and the contact surface. Now we take the edge of this contact surface, visualized by these red lines. It's actually only one line, and this blue contact surface is nothing else than a 1.5 twisted Möbius strip, which is also a nice fun fact. And now let's morph this rim of the contact surface continuously towards the center line, and what we see is that this rim of the contact shape shares the same topology as the closed trefoil knot, which is, at least for us, that was a very surprising observation that was already observed for an ideal configuration where they have double contact lines for an ideal configuration a couple of years ago, and we managed to, by taking this edge of the contact shape, to basically observe the same in a physical configuration. And I guess it's time to wrap up. I will give it over to Pedro.
Great. Well, this is all we have time for today. Maybe we can continue doing the Q&A next. So we showed you a series of problems where geometry, well, topology, geometry, elasticity, contact, and friction are really ingredients that are crucial to predicting the mechanics and cannot be ignored. At the moment, the studies that we have completed to date are rather fundamental in nature. But for the work that we have ongoing right now, for example, interacting with surgeons to understand what's a high quality knot, how the knots fail, we have to take all of these ingredients into account. And so I think we're setting up a basis for a toolbox for us to continue to address problems that have to date just been driven by empirical experience. Now, for the Q&A, had you come to visit us at EPFL, would probably walk down to the lake. It's about an 5 to 8 minute walk, and so beautiful view into the mountains and the surroundings. And so we'll finish by saying that we'll take your questions by the beach of the Pelican Park, as I said, 8 minutes or so from here. So yeah, thanks for listening, and shoot any questions that you may have. Thank you.
Right. So thanks very much, Pedro, Paul, for a fascinating tour of your city and your lab. So this is now open for discussion. Who wants to ask a question? I see Nunu wants to be first.
Nunu.
Hi. Thank you very much for your talk. Very clear. So I have at least two questions. The first one is related to the way you compute the contact details in the case of the Clasp. Okay, as far as I understood, you have two sensors, two fibers and based on the relative position between the two, you recover the shapes. But are you assuming that the cross section is always the same, or you are also computing changes in the cross section?
Yes, so maybe I can go that, and then Johanns can give a few more details, because he's really the one who developed this technique. So we do compute the changes of the cross section along the arc length. And what allows us to characterize the contact surface is this trick where we coated the rods with a polymer film that is very thin, but 15% denser, that the micro-CT can pick up. And from some tricks in image processing, we know what's in contact and what's not in contact. And in addition to that, we can characterize the changes in the cross-section. So it's just image analysis. We don't have to assume anything. We can see within resolutions of course of the pixels, the voxels, and so on, but we know what's in contact and what's not in contact.
Okay, my second question is related with the first part, the elastic capstone. What I found surprising is that the results you get is like if you have an effective decrease of friction, right? So in the simplest model, you have like Coulomb friction, and what you are showing for all your results is that the ratio between the forces is if you have a lower friction. But things like deformation, you expect that they lead to an increase in the effective friction between two surfaces. So do you have any, I don't know the Kirchhoff model that you used, but my point is just that because the contact is changing as a function of the force, or do you have any other insight? What is the mechanism that is leading to a decrease in friction, and why is it increasing when you increase the force with which you are loading the cable?
Okay, Grandgeorge, I leave that one to you. You're the expert.
Right. Yeah. So it is a really good question. I was surprised too, actually, at the beginning that. So the theoretical prediction would be up here. And we see indeed that as the diameter changes, well, then the force ratio changes. And actually the reason for that, okay, maybe, yeah, it changes for the plateau regime as we go far enough into the loading regime. And the reason for that is rather surprising, is that if the rod has a thickness, then you're not only imposing a force at the surface of the rod, I mean, you're imposing a force, but you're also inducing a moment that is distributed along the center line of the rod. So this frictional force, because it's tangential on the surface, it induces a moment. And actually this moment, it fights against the frictional increase of tension. Through some, in the equations, it becomes apparent. And also, well, it does depend on the diameter because it becomes a parameter that's important in these equations. And so really that's the key, is that the moment fights against the tension increase. And then the reason that's another interesting thing, the reason why it changes so much between, say, for this green curve, the reason why it's lower for lower loading is actually because the contact surface or the contact region is much smaller in the case of a small loading, whereas as you start pulling on both ends really hard, well then, and this interplay between geometry and friction as a function of loading is really what was interesting at the beginning for us, because this had not been studied. It's always considering that you pull really hard, whereas in some systems you're not pulling that hard actually, in the contact region is smaller. So you might overestimate a lot what you expect for the force transmission compared to what is actually happening down here.
But the case of the moment that you are explaining, for example, in rolling friction, you also have the moment, and this is increasing the effective friction. Why here is decreasing? Because I only know basic contact mechanics, but if I think about, for example, rolling friction, it's increasing the friction, not decreasing. And the mechanism is similar to the one you described. So,
right, but here, maybe, Nuno, remember that we have elasticity that is trying to counteract that moment, right? So in fact, that's working against it, and hence the difference between the simpler rolling friction problem that you highlighted, right? So, I mean, summarizing what Grandgeorge said, so a very important ingredient that is captured by this Kirchhoff-like description is the need to take into account the moment induced by friction into the rod model, point one, and then and that's included in the Kirchhoff-like description. Point two, when the wrapping becomes very tight, when the curvatures become tight, we have to take the geometric incompatibility of the two surfaces into account. That's what we did in the Clasp problem. And in that description, we still don't take cross-sectional deformation into account. And so we see that is coming in as a higher order effect that for more predictive theories, for example, to go beyond the simple contact lines into a distributed surface, you would have to take into account, but it's a higher order effect, right? So I describe them in rate of importance. And I think it also highlights the benefit of doing this very simple, very simple model experiments where you kind of throw in or kick in individual ingredients to see what matters the most.
Okay.
Does that make sense?
Yeah, makes sense. And so in your all your experiments, you fixed the thickness of the rod and you played with the size of the cylinder. What about the other way around? So what would you expect? Maybe from the experimental point of view, I understand it's not as easy as to change the size of the cylinder, but as you decrease the thickness, would you expect to keep seeing this initial decrease, but then all this effect that we are discussing will disappear? Or because the first one, as you explained, is more related to deformation, right? And changing in the contact between the two. Would you expect that this remains, or what will happen if you decrease the thickness of the rod?
Grandgeorge?
Right. Yeah, that's a good question, and I should actually have done it to prove the point that I will try to say now, is that as long as we work in the dimensionless framework, so we normalize everything by the relevant quantities. So here we normalize forces by EA, which is the actual stiffness or the characteristic actual force of a rod, and the diameter is normalized by the thickness. Well, then I would expect, purely say intellectually, I would expect that all the curves would actually fall on the same as long as I respect the same ratio of diameter of the cylinder to the thickness of the rod. And maybe to go along these lines, I will say that in FEM, I didn't put 2 millimeters or 3 millimeters. I did work directly on the normalized system that has no units, and then I plotted it here in the normalized system, and it seems to work well. Right. But to be really thorough, I think I should go ahead and yeah, perform experiments with other thickness.
a slightly alternative way to address this is to say that the mechanisms that we've been talking about do not excite characteristic length scales, right? And that's why the dimensionless framework works. And had we been, had been friction coupling with in some other way where there would be a characteristic length scale, of course, then it would become would start mattering. But it doesn't. At least at lower order effects of higher importance. And so I think, yeah, the non-excitation of characteristic lengths is what justifies what Paul just said.
Great.
Yeah, questions, Nuno? Thanks.
Thank you so much. Very clear. Thank you so much.
Okay, thank you. Any more questions? So I don't see any more raised hands, so maybe I can ask a question now. Concerning this capstone problem, looking at this picture in the top left-hand corner, it reminded me of something else. What would the relevance of this be, if any, to the dynamics of tracked vehicles, like bulldozers and tanks, that sort of thing? Of course, in that case, there's a substantial difference in that what you have going round the cylinder is not some elastically continuous object. It is rather something that's first it's piecewise, and second, it's not rounded. It's flat. But could this be in any way relevant? What you've done?
Maybe Paul, you can comment on an intermediate step of another thing that you could have asked regarding belts that are still continuous, and then yeah, the discrete, we don't have it, but I think it could be generalized. You want to comment on belts and then the discrete setting?
Yeah, so so we did actually, we also tried this system with an actual belt that was a metallic belt. So there was a ribbon that's used in conveying systems. So we really purchased it for engineering applications. And in this limit, the theory still works as long as the belt is a continuous elastic material.
Right.
But then it's true that for a piecewise linear material that acts more like a chain, then this theory would probably not work. And especially because it's, I guess in tanks and bulldozers, it doesn't necessarily work through friction, but really through grabbing through some sort of,
oh yeah, there's some teeth on the wheels, right, and rollers, and yeah, okay.
But the discrete systems is very interesting. I think you have to go back to the drawing board because you're throwing away elasticity, right? So essentially you have flexibility almost with a zero internal moment at the joints. And then you have to deal with the geometry. I mean, the geometric contact problem becomes different because you have these straight segments and you throw away elasticity. So I think it's a relevant problem that would force you to go back to the drawing board, but now with the guidance of what we've learned by the importance of contact and these other various things.
Okay, very good, thank you. Any more questions? So maybe I can ask just one last question. If I understood correctly, you treat your materials as neo-Hookean solids. That is, in terms of elastic behavior, they're fairly conventional. Have you ever tried doing something with, well, one material that I once worked on as a postdoc a few years ago, also at Cambridge, incidentally, which is, well, it's called liquid crystal elastomers, which are sort of fancy rubbers with very unusual and intriguing properties. So, well, who knows, someday you might like to try one of those.
Yeah. So we haven't played with active polymers like liquid crystal elastomers, or I mean, actually what we have played with is with magnetoelastic composites. So these rod systems that can be activated with magnetic fields. So maybe not as sophisticated as liquid crystal elastomers, but yes. So again, what's the challenge in those kind of systems? You have to go back to the drawing board at the level of the constitutive description to come up with the equivalent of the Kirchhoff equations for elastic rods that you saw, but now with additional terms that come from various field couplings. Okay, so maybe that's the first point. So magnetoelastic rods, yes, we have. More sophisticated, no. What Johanns can maybe comment about is on what about when you have plastic deformation in these filaments, right? And this is relevant relevant for surgical procedures. I mean, like fishing line, if you pull it too much, then it will neck and it will break.
Right.
Okay, Johanns, I was getting going with the answer here. What have you done on plasticity?
Right. So basically, we saw the frictional clasp, and very recently we started working on elastoplastic materials, and we could do like a similar experiment. We would take a capstone, but then there's elastoplastic filament around it, and we would basically use an air bearing or like ball bearings to really get rid of friction, and we would again measure a tension difference from one end to the other end, not a tension ratio, but a difference. But that on the side, we have a tension difference from one end of the filament to the other one, and so that's very interesting, especially if you think of combining these two, having friction plus an elastoplastic filament, and what you could do with these ingredients of tension loss.
Yeah.
Okay, thank you. Very good. So I don't see any more raised hands here, so I think it's time to wrap up. Right, thanks again. Thanks very much indeed for a fascinating tour of your lab and a fascinating narrative of your many activities, and we very much look forward to hosting you in person, hopefully in the near future. So this was the...
Fica o convite inverso também, quando estiverem por aqui ou se passarem por visita a Zurique ou aqui nas redondezas, são bem-vindos a uma visita real.
Muito obrigado, sim, uma visita real, de facto, por muito sofisticada e muito agradável que esta seja, de facto, uma visita real é outra experiência também.
Mais uma vez, obrigado pelo convite.
Obrigado, nós. Okay, so this was the last seminar in this academic year. So thanks to the speakers again, thanks to the audience for coming, and we'll be back after the summer break, hopefully sometime in maybe October. Right, so I do hope you all have a restful summer break, and we'll see you then. Recording stops now.